Hello again, MT1. Welcome to the continuation of our Part 2 discussion for the Module 8. For this session, we'll be discussing about amides. Let's take a look at our outline for amides. First, we will be discussing about the structure and the classifications, and then we'll proceed with the nomenclature or naming for the different classifications of amides. And then for the final part, we will be discussing about the uses of amides. Let's now proceed with the structure and classifications. So amides are a carboxylic acid derivative in which the carboxyl OH group has been replaced with an amino or a substituted amino group. So with the first part of our discussion for Module 8, we've discussed carboxylic acids and their derivatives, and mentioned there is amides. So amides simply differ from carboxylic acid by their OH group. Okay, later on, we'll be seeing the comparison between carboxylic acid and amides. Amides are similar to amines and can be classified as primary, secondary, and tertiary. This means that there are also different classifications for amides. So we have a primary amide, secondary amide, and tertiary amide. As you can see, we have here a double bonded O. Okay, so how do amines and amides differ from each other? Amines only contain carbon, nitrogen, and hydrogen, while amides contain the four abundant elements, which are carbon, hydrogen, oxygen, and nitrogen. So as mentioned a while ago, amides are derivatives of carboxylic acids, wherein carboxylic acid's functional group is COOH. Amides, on the other hand, they replace the OH part of the carboxyl group and replace it with an amino group, which is can be CO, which is C double bonded O, and then we have NH2. Okay, here is our amino group, and here is our carboxyl group. I mean carbonyl group. Let's proceed with classifying amides. Classifications of amides are similar, very similar with the classifications of amines. So primary amides, secondary amides, and tertiary amides are based on the bonds that they have in their nitrogen element. So for primary amides, we have here the nitrogen is bonded to one hydrocarbon and two hydrogen atoms, which is very similar to how amides are. But their only difference is that in amides, we have a double bond O present. The other name for a primary amide is an unsubstituted amide. For secondary amide, it is the nitrogen is bonded to two hydrocarbons and one hydrogen atom. There is one hydrogen atom present in here. For tertiary amide, on the other hand, at this point, we don't have hydrogen atoms anymore, and all of the bonds of nitrogen are bonded to a hydrocarbon. Secondary amide is also called as a monosubstituted amide, and the tertiary amide is called a disubstituted amide. Shown here is the comparison between the classifications of amides and amides. As you can see, they are very similar. Only difference is their double bond O for amides. Let us now proceed with the different examples of amides, starting of course with our simplest amide, wherein it is simply an unsubstituted amide group with a hydrogen attached to it. So this is our unsubstituted or our primary amide functional group and our hydrogen attached to it. Next, is an amide with methyl groups. There are two types of amides with methyl groups, and their difference depends on the position of our methyl group. We have one with methyl group attached to the carbon atom, wherein it looks like this. So for our unsubstituted or primary amide, we have a carbon double bonded to O, and then we have an NH group. Okay, and then the methyl group for this one is located in our carbon atom, or is bonded with our carbon atom. So this is CH3. And then there is also one wherein the methyl group is attached to our nitrogen atom. So we have our carbon group bonded with nitrogen. There's also a hydrogen, and then our methyl group. Now with this difference, even though they both have a methyl group, the first one is a primary amide and the second one is a secondary amide. Remember, the classifications of amides is that the nitrogen for primary amides have two hydrogen attached to it and one hydrocarbon or one carbon attached, while secondary amides have one hydrogen attached to it and then two carbons on the other hand. So these are both different types of compounds. Next that we have is the simplest aromatic amide. So this one is a benzene ring with an unsubstituted amide functional group. As you can see, unsubstituted or a primary amide has two hydrogen atoms attached to it. And then we have here a benzene ring. Now in amides, unlike in carboxylic acids wherein they cannot exist in cyclic forms, cyclic amides are possible and they are what we call as lactams. The ring size in a lactam is indicated using a Greek letter. So as the carbon increases in the cyclic amide, the Greek letter also changes. So alpha lactam indicates that there are two carbons in our cyclic amides. Beta lactam indicates that there are three carbons located in our cyclic amides, and so on. We're now done with discussing the structure and classifications of amides. Again, all you need to remember here is that amides are a derivative of carboxylic acid wherein the OH from the COOH of carboxylic acid is replaced by a amino group, which is NH2 if it's unsubstituted. Let's now proceed with the nomenclature or with naming of amides. So we have here both the IUPAC and common nomenclature of amides. So the name of amides are based on the name of their parent carboxylic acid. Since they are derivatives of carboxylic acid, we will be basing or we will be getting the names of these amides from our parent carboxylic acid. So here are the rules. First, the ending of the name of the carboxylic acid is changed from ic acid if it's from the common name, or oic acid if it's from the IUPAC name, to amide. Okay, so we will be changing the suffix of the carboxylic acid parent compound to amide. For example, if you have a benzoic acid, we will be dropping the oic acid and it will become a benzamide. The names of the groups attached to the nitrogen, if it's a secondary and tertiary amide, are appended in the front of the base name using the suffix or prefix N as a locator. So this is also similar to how we name the secondary and tertiary amine. We will be using N as a prefix locator, wherein it indicates that the other group or other carbon group are attached to our nitrogen. Again, on our example, we have benzamide from benzoic acid. And then another example is a 3-methylbutanamide. As you can see here, we have our amide group. Here is our amide group. We have a carbon here and then 3-methyl because we have one methyl substituent, and then butanamide because we have 1, 2, 3, 4 carbon chain length. Okay? This is very easy and quite similar with how you also name the other compounds. Let's have one example. So for this one, you have your nitrogen, and it is a secondary. Okay, it is a secondary amide. How did we know? Because there is only one hydrogen attached to our nitrogen, and then there are two carbon groups. Locate which is the longest carbon group. Okay, this is similar to how you name the secondary and tertiary amines. Locate the longest or the largest carbon group, which is this one. Okay, and then we will also be choosing this one because this is where the double bond O is located. This is our parent carboxylic chain, or this is where the parent carboxylic acid is from. So this is now 1, 2, 3. We have 3 chain carbon length. So since this is a 3 carbon chain length, this is a propanoic acid. We will be dropping the oic suffix and change it with amide. We will be dropping the oic acid and then change it with amide. So this will now be propanamide. And then for the other carbon group, which is a methyl, we will be putting N in front of it to indicate that its location is bonded to the nitrogen. So we have N, methyl propanamide. Let's check if our answer is correct. So we have named this compound as N-methyl propanamide. Let's take a look at the next one. Hopefully you're following through, or you're at least trying to name it on your own. You can pause the videos so that you can have more time to name them. So for this one, we have 1, 2 carbon chain length. So this is 2 carbon. So that's ethanoic acid. Change the oic acid to amide. So we have now ethanamide. We don't have any more substituents, so we can simply name this compound as ethanamide. The next example seems complicated by simply looking at it, but do not be overwhelmed. Okay? Let's try to find our longest chain first. So we have 1, 2, 3. We also have here another hydrocarbon. So this is now a 3 carbon chain length, which is a propanoic acid. Changing oic acid to amide. So this is propanamide. And then let's start naming now the substituents. So on carbon number 2, we have chlorine and a methyl group. So this is chloro, and this is a methyl. So we will be naming it and identifying the substituent by putting them in front of our parent chain name. So this is 2-chloro, 2-methyl propanamide. Let's check if our answer is correct. We have 2-chloro, 2-methyl propanamide. Again, do not be overwhelmed with how the structure of the compound appears, but try to look first for the longest chain and then proceed with then identifying your substituents. For our next and last example, we have another secondary amide. Because, again, there is only an existence of one hydrogen attached to our nitrogen. So our parent chain here will be this one. Then we have the other group as methyl. Our parent chain identify the longest chain. So we have here 1, 2, 3. You can also go this way. 1, 2, 3, 4, 5. So since this is our longest chain, that is what we will follow. This is a 5 carbon chain length, which is a pentanoic acid derived from pentanoic acid. Change the oic acid to amide, so this is pentanamide. And then determine its derivatives first. We have here another methyl group located in carbon 2. So this is 2-methyl pentanamide. For the other carbon group attached to nitrogen, this is now N-methyl. Now, since we have 2 methyls as our substituents, we can simply put these 2 as dimethyls. Can simply indicate them as dimethyls. And then for their location, we can separate them by using N. And then for this one, we have 2. So let's check if our answer is correct. We have N2-dimethyl pentanamide. So you don't need to have a separate term for N-methyl and 2-methyl pentanamide. Since both of them are methyl, you can simply combine them since they are the same. And then just indicate their locations, which is N and carbon 2. We're now done with the nomenclature of amides. Let's proceed with the different uses of amides. Here are some selected amides and what are their uses. First we have is urea. You might have heard of it when talking about anatomy. Urea is a 1-carbon diamide, which means it has 2 amides at both ends of the compound. It's a water-soluble white solid produced to eliminate waste nitrogen. Melatonin is also an example of an amide. It is a complex amide and a hormone that is produced in the pineal gland. It regulates the sleep-wake cycle. Acetaminophen. This is a synthetic amide and is considered as a top-selling over-the-counter pain reliever. This is a derivative of acetamide. So by tweaking some of the properties of acetamide, we can produce acetaminophen. Barbiturates, on the other hand, are cyclic amide compounds, and they are heavily used for prescription drugs such as sedatives and tranquilizers. These are just some of the uses of amides. So we're now done with discussing both amines and amides. You might want to take a short break before continuing this video and before we start discussing the physical properties and reactions of both amines and amides, along with the discussion of how to prepare amides and quaternary ammonium salts. Let's now proceed with the last part of our Module 8 lecture discussion, which is about physical properties and reactions of both amines and amides. For this part, we'll also be discussing about the preparation of amines and the quaternary ammonium salts. Let's start by talking about both the odor of amines and amides. We will also compare them with each other. Let's take a look at this table. We have here sample compounds for both amines and amides and comparing all them with ammonia. So as mentioned earlier in the first part of our discussion, ammonia or NH3 is an inorganic compound that is usually in a gas form and it produces a strong, sharp, and pungent odor. It's very notable, very foul-smelling. Amines, or in this example, dimethylamine, if it's a low molecular weight amine, It has a less sharp odor than NH3, though it is still notable as a pungent, foul-smelling one. It is not that sharp as ammonia. High molecular weight amines, on the other hand, smell like raw fish. Okay, they produce a raw fish odor. Acetamides, on the other hand, if they are pure, okay, they are odorless. But if they are reacted with a methyl acetamide and produce an impurity, it can produce a dead mouse-like odor. Okay, so it seems that the nitrogen greatly contributes with the foul-smelling odor of some compounds. The foul odor of amine is due to the amines released by bacterial decomposition of proteins. Okay, so we can usually observe these amines when there is a bacterial decomposition. The one responsible for the unpleasant odor of decaying flesh is what we call putrescine, which is a kind of polyamine. As the proteins are continuously broken down to smaller components, the bacteria starts to increase or to excrete gases and organic compounds. And one of the organic compounds that it releases has the functional group amine, which is, as mentioned, is putrescine and cadaverine, which carry the noxious odor of rotten flesh. And so this decaying flesh, this very foul-smelling odors, can sometimes be caused by different types of polyamines. Let's now take a look at the solubility of these two organic compounds. So generally, they are soluble in organic solvents and in water. Low molecular weight, or those with lesser carbon atoms, they are soluble in water. So if the carbon atom is 6 and below, they can be soluble in water. Those with higher molecular weight, on the other hand, are sparingly soluble. Okay, they are quite insoluble in water. Primary and secondary amides are less soluble than amines. Tertiary amides, on the other hand, have low solubility in water, so they might tend to produce like precipitate. Let us take a look at this example of the table comparing ammonia with dimethylamine and acetamide. So in this one, it's showing its solubility in water. So ammonia is miscible in water with the pH which is basic. Methylamine is again miscible in water and it also has a basic pH, which means it's a weak basic to be exact. Acetamide, on the other hand, is soluble, okay, and its pH is neutral. Kindly keep in mind that acetamide is the amide form of acetic acid and exists in white crystalline solid form if it's pure. Comparing the pH of both the dimethylamine and acetamide can give us the idea that amines are basic and amides are neutral. Now, why is the pH of amines basic in nature while amides are neutral? This is because of their structures. The electron pair is mainly localized in nitrogen of amines, meaning they have much higher chances of being acidic or basic. Unlike with amides, the electron pair is delocalized to the carbonyl oxygen, therefore getting a much lower pKa value compared to amides. It is delocalized in the oxygen so that the compound would be a stabilized cation. Because of the existence of the oxygen in amides, this is the cause of amides having a lower acidity and becoming neutral in comparison with amides. So those are the basic physical properties of both amines and amides. Let's take a quick look on how the preparation of amines and quaternary salt or quaternary ammonium salts happen. So in the preparation of amines and quaternary ammonium salt. This is also what we call the alkylation of amines. Alkylation of amines happens in the presence of base. This simply means that a primary amine can be further alkylated to give secondary amines and tertiary amines. By undergoing this process, we can simply produce secondary and tertiary amines from the existing primary amine that we have. Quaternary ammonium salt, on the other hand, this is where all four hydrogens of the ammonium ion are replaced by the organic groups, meaning there is no hydrogen existing anymore and all of them are replaced by organic groups or the alkyl groups. So here is the visualization of it. So we have ammonia. If you add an alkyl halide and then catalyzed with a base, it will produce a primary amine. If you add an alkyl halide to a primary amine which catalyzed into a base, it will produce a secondary amine. And then adding it further will produce the final, which is a quaternary ammonium salt. Here is another visualization of it. Again, primary amine. If you mix it with an alkyl halide, it will produce this product. And then if you added or catalyzed it with another strong base, it will then further react to produce a secondary amine. So this is simply the alkylation of amines. All you need to remember here is that primary amines can be further alkylated to give secondary amine and so on. And then we also have to remember the meaning of quaternary ammonium salt, wherein no hydrogen exists anymore and all of them are replaced by the organic groups or alkyl groups. We're now done with the discussion of Module 8, Part 2. We've finished discussing amines, amides, their structures, their classifications, and their namings, along with their uses and their importance. We've also discussed the physical properties and the reactions, which is useful in observing them and in differentiating them. Here is the reference that I've used for this module. If you have any questions for the part 2 of Module 8, please do not hesitate to message me on my Canvas inbox or to email me. If it's an urgent matter, I'm also allowing you to message me on Messenger. That's it for our lecture part for Module 8. Thank you and God bless.